Tov, shalom everyone. For everyone that survived a long day, thank you for being here. I'm going to speak on, like it was presented, an important toolkit or set of algorithms and data structures that every data scientist need to know about and need to care, I guess. So what are the type of processing that we are seeing or using in big data analytics? Well, first of all, there is the offline processing. The offline processing, usually a batch process done periodically. And we use mainly Hadoop or MapReduce algorithm to scale it. We have certain challenges in this, but the more interesting places where we use probabilistic data structures is with nearline and online algorithm, or nearline and online computation. Nearline is basically when you do incremental processing. This is a side process that runs along basically a more real-time computation in order to compute, for instance, alerts and other events that you can process them asynchronously, but you still have to react quite fast. And then you have the real-time or the online, which is stream-oriented. The latency that is expected is very short, and you need to scale through shell, nothing, or stateless instances. So why should we care about this? I mean, as developers, as data scientists, we usually used to have the standard data structures that we have in our standard SDK, standard libraries, like in Python, in R, or whatever language, or Java, or whatever language that we use. This is the linear list, the hash map, and the tree, and many data structures that we use, and they work quite well, and we are used to use them. But why do we need, or what happens that we need they are not working well when we go and work with streaming of data or with large scale data? Mainly when the data exceed our memory, then we suddenly, we are not in Kansas anymore. I mean, we cannot use what we, the tools that we already, and the tools, the data structures that we already using regularly, they're not working anymore. And just to give you an example, for instance, if you have to calculate in your data or over your data the statistical mean, then it's usually very easy to do it. You just need to aggregate a sum and to calculate or aggregate in the count of items that you have in the list, and that scales very nicely and very well. But if you have to calculate the median, then this is becoming a more challenging task, because this is something that you cannot calculate on the fly. You have to, in the standard algorithm, you at least have to sort the data so you can find the median, and I'll show you later on a way to do it in a more efficient way if you can, or if you are ready to trade off on something. And what actually you have to trade off about? Usually, if you are willing to trade off accuracy versus approximation, and you are ready to get only approximate result, in many cases you will get a much more efficient data structure or algorithm which scales quite nicely and works very well with big data. So I'll give in this presentation several examples of several such data structures for several use cases that might be interesting for you, you might be encounter using your projects. So I will start with something quite simple, and this is data sampling. Usually you need data sampling, for instance, if you have, let's say you have a model that, or a data set that you want to train, and your model with, and the data set is quite large. You have your library, your scikit, or whatever libraries that you use, or R, which uses or which runs the model in memory, and you have a data set that is larger than your memory. So what you can do, you can sample the data. So you can take a uniformly distributed sample of the data and use this instead of the entire data. And usually in many cases it works quite well, and you don't need to go to the way to use multi-instances, algorithms, and things like this, which are becoming more and more common, but still are more and more complex. So how you do the sampling? There are several ways to do the sampling, and it depends on the type of sampling that you need. So hash mode technique, this is one technique, and actually it's something that we use, I am using in interview questions, and I'm amazed on how few people do get it correctly. But basically the idea is that if you have to take a sample of a population of, for instance, you get an event, and each event is identified by a device ID or a user ID, and you want to get only 5% of the population, but you want that the population that in the sample, you will get all the events for that population. So what you actually do is you can take a hash of the ID, and then take a modulo 100, for instance, of the hash, if you need, for instance, 5%, and if the value that you get is less than 5, then it should be in the sample, and then you pass the event. Otherwise, you can ignore the event. So that's one technique. Another technique is if you have to sample, but you have to sample k elements out of out of your data set. So what you do, there is an algorithm called the reservoir algorithm, and the intuition for it is quite simple. Basically, if you have only one element, you actually keep the first element in the stream of data that you get, and then each subsequent element, you kind of select randomly a number between y1 and I is the sequence number of the element in the stream, and if the number that you got is I, then you take the element and you replace it. And if you do the calculation, you will see that you actually get it distributed. But one, of course, is not interesting. Let's say that we have k element. So again, it's easy to extend. Basically, you take the first k element and put them in your buffer of k elements, and then every additional element based on its distribution, on the number in the sequence you already have, and you can see here the algorithm you can use and put it into the element if it meets the probability of that element. Another technique to do is if you have to do a map reduce on a large data set and you want to sample the data set. So what you do in this case, there is a nice trick here. You can actually take a hash of your data in each instance that runs, or each mapper that runs the data. And when you actually sort the data in each instance separately, and then you send to the reducer, or you select the top k in sort order elements from your data set. And then in the reducer, which got all the elements from all the different nodes, you just sort again and take the first k or the highest order k items from the list. So we spoke about sampling. Another important data structure or use case that we have is a set membership. Think about a problem. You have to find a needle in a haystack. How you do it? Or to be more specific, you actually have just to know if the needle is in the haystack, yes or no. Now, if you're expecting an exact answer, then tough luck. I mean, it's not easy. But if you can, as I said, trade off, and you are ready to give away something, and you are okay with getting probably yes with a high accuracy, but not exactly, and definitely not as an exact answer. So if the needle is not in the haystack, you will definitely get the correct answer, it's not there. But if you get the answer, it's probably there, then it's probably there, but there might be also false positives. So a data structure that provide this capability is called the Bloom filter. And the idea for Bloom filter is quite, I mean, the mathematics behind this is evolved, but the idea is quite simple. Basically, you take an array, or you have an array of m bits. Each bit represents an item in the data structure, and you have several hash functions. So now when you get a value that you want to enter into the data structure or into the set, you actually run each of the hash function. Each of the hash functions give you a number between 1 and m. M is the size of your bitmap array. And you set the bit at that reference to 1. And when you get a query for a value, what you actually do is, again, run the same hash function, all the k hash functions, and if at least one of them returns to you a value of 0, you know definitely that the values that you are looking for was not entered into the set. Otherwise, if you get all of them 1, you probably think that it's okay to assume that the value was put into the Bloom filter. The nice property about the Bloom filter is that you can control actually the error rate, or the allow probability of the error. And here are a few examples. So for instance, if you are looking for a precision of 1%, and you have 1 million, you want to store a set of a million items, you can do the math, and you will get that you'll need about 1 to 2 megabyte of RAM, of space in RAM, and you need 7 hash functions to do it. And if you compare it to a standard hash function, or standard hash map structure, you see that it's much less space than what you would normally use. And actually, a real-world example from what we do at MyThings. MyThings, among other, what is a part of real-time bidding, or is using the real-time bidding infrastructure. And actually, I don't know how many of you that are not in the ad stacks. I mean, most of the time you are not aware of what's happening behind the scene when you come to a site like CNN or TechCrunch, and you are presented with a banner. But actually, behind the scene there is a very huge and complex infrastructure that is intended to bring to you the correct or the most targeted ad for you. And basically what the site is doing, it's calling a real-time bidding exchange, and that exchange is calling or is broadcasting a request for a bid for many buyers, and MyThings is one buyer. So we are getting about tens of billions of requests a day. Now, most of the requests that are coming to our servers are coming with a user ID, and most of the users, we are not interested in those users, or we don't have anything to offer to them. So for instance, 97% of the requests are not of interest to us. And those requests need to be to be responded within a very short latency. So we have less than 40 milliseconds to answer each request, and at that time we need to retrieve the user from the database, calculate all kinds of machine learning algorithms, etc. So if we can just identify that the user is not of interest to us, then we can just send a no bid, and without going through the entire process of going to the database to see that the user is actually not there, etc. And what we do is actually employ a Bloom filter. So each of the servers that receiving the bid request, and such a server can handle thousands of requests a second, just have a Bloom filter cache where we update all the users that we do know, and then they can look on this cache, see, or this Bloom filter cache, see if the user is in the cache or not. If it's not there, it can actually return the bid or return a no bid because we are not interested in this bid. There is, for those of you who really wants to implement a Bloom filter, there is actually a new type of data structures called Cuckoo filter, which is basically or presented as practically better even than a Bloom filter. And the interesting property for the Cuckoo filter is that it allows dynamically adding and removing is an important, I mean, if removing an item from the data set dynamically is important for you, then you should definitely look on the Cuckoo filter. The name Cuckoo filter, by the way, coming from a trick or a hash technique called cuckoo hashing, which actually mimics the way a cuckoo offspring is kind of pushing the eggs from the nest in order to make space for itself. So we'll look on another use case, and this is frequency estimation. So let's say that you want to estimate, you have a stream of data and you want to estimate what's the frequency of an item. And so one way, of course, is to create a hash map and put all the items there with a counter. That would be, the way or the standard way of doing it, but it's quite expensive in terms of memory consumption, etc. So there is a technique called the count min sketch, and it's basically quite resembling a Bloom filter, but the use case is for frequency counting. And the idea here is that you have a data structure which contains actually W columns and D rows, and you have D hash functions. And when you get a new value, like in Bloom filter, you run the hash functions for this, all the hash functions for this value. Each hash function actually gives you a different column on each of the rows, and then you just increment by one the counter at that column. When you want to know the frequency of a number, you get a value and you want to know the frequency of this, you do, again, the hashing over all the numbers. You get the counters from each of the row, and basically you just need to take the minimal counter between all of them. And again, with a very good probability, you are assured that you got the frequency of that number. Now this is very useful actually to find the top k elements within a list. So how you find the top k elements? Let's say again, you have a very large stream. You want to hold, for instance, it's a stream of all the users that are visiting your website, and you want to know who are your top 100 users, or which are the top 100 IPs where you get traffic from, because they might be bots and not real users. So what you can do is actually use this data structure, the count min sketch. Each time there is a new value, you just put it into the sketch. You also maintain a buffer or heap of k elements, and for each value you enter it to or you increment its value in the min count sketch. Then you retrieve back the values that currently have in the sketch, and you replace and you use a kind of a threshold like KL multiplied by n to decide if to replace that number within the heap of k element. And at the end, you are promised with a very good probability to have the top k elements in this heap. I promised to you in the beginning to show how you can do median in a more efficient way. Again, if you are ready to trade accuracy with approximation, actually I give a bonus, and it's not just a median, but actually any quantile. And there is an algorithm, actually it's quite a new algorithm. I mean, it was invented in 2013 by a guy named Ted Dunning from MapR. And actually it uses a very smart representation of the cumulative distribution function of the stream. It's dynamically built this cumulative distributed function, and using a nice technique to introduce the, or to use the, to find the interesting spots within this cumulative distribution function. And the T-digest is basically very, I mean, it's on GitHub, so if you, for instance, need to implement your own either quantiles or a median on a stream or in a MapReduce situation, that would be a very nice algorithm and very effective algorithm to use. And you only need a very small data structure. Probably you can see here, but maybe the data is too small. But for sets of hundreds or thousands or tens of millions of data, you need about 20K of data structure space in order to keep the data. So last but not least is how to count distinct values. Let's say that you have, again, a stream of data, and it's, for instance, users that are visiting your website, and you need to know how many distinct users or how many distinct devices you have seen in the last day or a month or a week, etc. And basically, it's not an easy task. I mean, in many cases, or if you want the standard or the accurate answer, you need actually to have all the data and run across all the data in order to calculate or find the number of distincts for a certain period of data. But if you're ready, again, to trade accuracy, there is a very nice algorithm. It's called the hyperlog-log, and it uses a very efficient data structure. For instance, in 1.5K and with an allowed error of about 2%, you can actually maintain 1 billion distinct values. And it has nice properties as a data structure. So you can, for instance, take two such structure. Each one contains the distinct counts on a different stream. And then you can, for instance, merge them together. Let's say, for instance, that you keep on each data structure, or on each hyperlog-log data structure, you keep 1 day of distinct count for that day. And now you want to know how many were in a week. So you can do a union, or you can take the data structure and run a union on all those, use this union operator, and then you get a data structure which actually gives you the distinct count for the entire week. So that's a nice property of it. You can also do the intersect. Unfortunately, you can only calculate the intersect, but you cannot. But you will get you will not get a new data structure because then the data structure does lose its capabilities. But if you take the calculation, like you take the distinct and you subtract the union, then you can actually calculate the intersect of both of them. So I will, to conclude, I just gave you a glimpse of several use cases where if you have the traditional way of solving this problem, you would go to algorithms that are quite complex when you have very large data set. And if you have such algorithm, try to think or try to see or search, and for this we have Google, to search for a probabilistic algorithm that might save you a lot of, in many cases when you do streaming, you don't need the accurate result all the time. You already, for instance, if you are speaking about a distinct count, then a distinct count with an error of 2% is very, very good for many applications. So if you have such a problem, look for a probabilistic data structure and you will be amazed to find that there are solutions which might save you a lot of complexity, infrastructure, and space, time, etc. Thank you.